numbers. Peter Shor went about and invented his error correction algorithm and came up with the threshold theorem, which basically says if you can manipulate little quantum bits with enough precision, then you can build a very large quantum computer and do whatever you want with it and basically construct any quantum computation you like. And so now, sort of almost 25 years later, we have a number of companies that are building quantum computers using different physical implementation of qubits. And of course, there is a boom, there is lots of funding available, and students are working in quantum information are being sought over by the companies. Of course, good students, anyway. Okay, so this talk is about quantum error correction. And even though Peter Shor invented the first quantum error correcting codes, it was Daniel Gottesman who sort of worked out the detailed theory in his thesis for quantum error correction codes, of the important class of the codes, which is called stabilizer codes. And basic idea is you have a bunch of Pauli operators. And so Pauli operators are, you think of collection of spin 1/2 particles or two-level systems. And so Pauli operators are generalizations of Pauli matrices to multi-spin systems. So that you can have a product of Pauli sigma x on one spin and Pauli sigma x on another spin. So these are examples of Pauli operators. And so if you have an abelian group of Pauli operators, then of course you can diagonalize these operators simultaneously. And Pauli operators have nice property that Hermitian Pauli operators have eigenvalues plus or minus 1. And so the code, if you have such a group, which is called stabilizer group, the code is a common eigenspace with plus 1 of all of those operators. So it's really very simple if you know the basics of quantum mechanics. You know that commuting operators can be diagonalized simultaneously. And this is the basic information that you have to know about the codes. Of course, the difficult thing is how to, in practice, construct the useful codes. And so what happens is whenever an error happens that anti-commute with one of the generators of this stabilizer group, it throws the wave function into an orthogonal space. And the goal of designing a useful code is such that likely errors would throw you out into an orthogonal space. There are many of these orthogonal spaces, and you have to construct a code that covers as many likely errors as possible. And in the simplest case, if the small weight errors, the errors that happen on just a few qubits happen most likely, are most likely, you want to design a code that, for any of these small weight errors would throw you away into a different space. And so the parameters of the codes are the number of qubits, this is n, total number of physical qubits, the dimension of the code, this is the number of encoded logical qubits k, and the distance of the code, which is how big an operator you have to have that does not throw you in orthogonal space, but would instead act within the code and would spoil your quantum information. That's the idea. Okay, so let me go back. So Peter Shor invented the concatenated construction, which is, again, very well understood by physicists, because you can think of this as renormalization group. So you encode one qubit into 5, and then you do something with them. Then you take 5 copies and encode each of these logical qubits again into 5, and then you do it several times over. So you encode one qubit in 125, 625, etc. So you have a tree of like Russian doll codes, which if the errors for any little sort of elementary operation are small enough, and Peter Shor was smart enough to work out how to do this nice, if you do everything correctly in a fault-tolerant fashion so that you don't propagate errors, it turns out that you can ensure that errors get smaller and smaller the deeper into the encoding you go. And this is, his threshold theorem. Now, it turned out that this construction is sort of very unstable. It's very hard to operate. Much more stable kind of codes was constructed by Alexei Kitaev, which is called the story codes or the surface codes. And again, topological order. This, there is a lot of physics. In physics, it is a well-known model of topological order. And so, but sort of there are big advantages in sort of not only for physics, but also of these codes, but also for quantum information. So if you want to build a quantum computer that operates on the surface code, it is going to be a local, so where every qubit just has to operate locally. You don't have to worry about that much about fault tolerance at every measurement as with concatenated codes, because there are fewer things to break. And then, sort of very importantly, if it's topological. So if you cut a hole in your lattice grid, and then you start moving this around, the hole will have an associated qubit with it because it's topology. Topology changes when you cut a hole, right? And so there are protected gates where you have two different excitations. You can braid them around, and you basically have a subset of important gates, namely the Clifford gates. So the biggest difficulty, the biggest problem with the topological codes is that they have huge overhead, because a big block of code will encode just one qubit, and you have to have a lot of logical qubits in order to do useful computation. And so basic question is, can we do better than the surface codes? And there are constructions. Let me illustrate. So this is the construction of the two-dimensional toric code. So you have, the plaquette operator and the vertex operators, which are represented by these little pictures, and you can sort of ensure that however you move them on the lattice, the overlap between, you always overlap in an even number of positions, and that ensures the commutativity. So if you have two Paulis that anti-commute, if you have XX and ZZ, pairs of them, they would commute together. And so similarly, there is a construction of hypergraph product code, which was constructed in 2009. And you see, you introduce a little bit of non-locality, and the price you pay, your topological strings get binary modulation along the line. And so instead of the continuous strings, you have a modulated strings, which are nevertheless have the same stability. But because they are modulated, if you shift them by 1 or by 2 horizontally and vertically, you have a linearly independent string. And so as a result, instead of just 2 qubits, which is the related to the genus of the torus, in the same geometry, you get 18 qubits, because here you can shift them sort of horizontally and vertically. And similarly, there are higher dimensional versions of the codes, and you can also generalize these product codes to higher dimensions, to any dimensions you like, and they have nice property. You have surfaces, etc. So there are sort of nice properties. But this talk, so these are constructions. But in addition to constructions of these non-local codes which encode many qubits, there are sort of other benefits. Okay, so anyway, so let me first of all explain this theorem in 2 dimensions, and this is the theorem of, these people. So the number of encoded qubits k times d squared is less or equal than L squared times n. So here L is the range of the stabilizer generators in 2 dimensions. So for the toric code, L equals 1, and so you basically, toric code saturates this bound. So you have 2 times 7 squared is 98. For hypergraph product codes like these, you also saturate this bound. So, well, almost saturate this bound. So you have somewhat smaller distance. You have more qubits, but and the reason why you have more qubits is because the range L here is bigger. Okay, So there are two examples, two basic examples there are of such codes. So one example is hyperbolic codes. And so what it's basically a surface code, but on a highly curved space. So imagine you have a hyperbolic tiling, like 5-5 tiling, but then using the tricks of the group theory, you can have a quotient of the symmetry group and instead generate a finite surface, which will have, very complicated topology. It will have a very high genus that is proportional to the number, to the total area. And so these codes have finite rate. So for example, for 5-5 tilings, you have rate equal 1/2, but the distance goes like logarithmically in n. And then there are these algebraic constructions which are illustrated here. So I have a couple of generators which are sort of non-local, and then sort of the logical operators acquire some modulation. Okay, so basically the Tori codes have been around for a number of years, and so in addition to construction, they offer great flexibility, and the flexibility is related to defects. So if you make defects, you can, like this one, so this is the smooth defect, this is rough defect, and so each of them carries logical operators, and the distance of this particular defect, it's a perimeter, and the dual distance is this distance to the edge. So similarly here, there is a perimeter in the dual space, and then again, distance to the nearest edge. And so if you move these defects around, then these string operators that attach to each defect would intersect, and that would correspond to the C0, operation on the encoded space. And so what I'm doing now, I'm trying to construct these defects for more general class of codes, which are not necessarily local LDPC codes, low density parity check. And so the condition is that I have Pauli generators, each of which have some bounded weight W, okay? And I want to construct holes or analogs of the holes which would support the logical operators of sufficiently high weight so that I could operate with these operators fault tolerantly. Okay. And so the question is, can we construct such defects? And most of the sort of remaining 10 minutes I have, or okay, I will talk about construction. Can we satisfy the condition of that the distance or the perimeter or analog of the perimeter has to be much, much bigger than the weight of the generators? And then also the last question is, can we do gates by sort of analogs of braiding of these defects? And how you can imagine doing this if you have a non-local structure without a well-defined geometry? So these are the kind of questions that are important today. Okay. So the construction, I will, this is the actual construction, but here I want just to focus on the assumptions. And so basic assumptions are this, that we have a large distance LDPC code. So the large distance, I mean that the smallest operator that acts non-trivially within the code has very large weight, okay, which is much, much bigger than the weight of the generators of the stabilizer group. And then I will also make a simplifying assumption that this is a CSS code, meaning the generators are only of the X kind or the Z kind. So, one example is, of course, is the Tori code, where you have the plaquette operators, which are, for example, all made of Pauli X's, and the vertex operators, which are made out of Pauli Z's. Okay, and then I will also assume, and this is assumption that I don't know yet how to get rid of. I think I can, but not yet. I will also assume that if I take a product of generators, which is bigger and bigger and bigger, the weight of the resulting operators must grow with the number. So this is the weight of a product of m generators have to be an increasing function of m. So this would be the only assumption that sort of tells me about the structure of the codes. Okay, and so here is how the defect construction works. So I have two pictures, one for the surface code, and the other for this, hypergraph product code with weight 6 generators. Okay, so what I do, I select a position, select a qubit, and basically I want to remove that qubit, but I also want to keep my stabilizer group commuting. Okay, and so when I remove the qubits, so I replace, what would be an incomplete ring, I will replace it by a product of two plaquettes. So I have now a bigger plaquette. Whereas for the blue operators, I just remove this point, this yellow point, that qubit that I'm removing, I just reduce the weight of the blue operators. And so this is always be the case. And so, okay, and so this ensures the commutativity because, this qubit I am going to remove from any of the generator of the group, whereas I'm going to cut it, from any red generator of the group, which would be Pauli X, for example. I'm removing this qubit, whereas from the blue generators, I just cut it out by reducing the weight. And so the statement is that by doing this step by step, I'm preserving the structure of the group so that my operators continue to commute, and I still have a quantum code as a result. And so in the case of this hypergraph product code, I can do it. I can select any pair of my generators which have a common qubit, and then I form a product, and then I remove this qubit out of consideration. Okay, and I continue doing this. So in the case of qubit, I'm making an increasingly big cut. In the case of the toric code, in the case of the hypergraph product code, I'm removing one qubit and then the other. And so as a result, my stabilizer group is acquiring this very big weight generator that, that is getting bigger and bigger as I do these steps. And the condition on the, because I'm removing these qubits, there is no way I can sort of cut it back to the original generators. And then the condition on the weight of the operators, that the weight of the product has to increase with the number of generators, tells me that in the entire group there are no generators that are of smaller weight than this one. Okay, and so what I'm going to do, I'm going to promote this operator and say I remove it from the stabilizer group and now make it a logical operator of the additional qubit. Okay, and then I have to add, I have to come up with a, if this is logical X, this cycle, I have to come up with the conjugate operator which anti-commutes, which anti-commutes with it, and it will serve as logical Z. And I can always do it using linear algebra, basically, or Gram-Schmidt orthogonalization procedure. And now, if I have the code of sufficiently large distance to begin with, I can also prove the lower bound on the distance, which would be sort of analog of this distance to the nearest edge. Okay. And so this answers the two questions. Yes, we can construct such defects, and yes, we can satisfy the LDPC construction. Okay. Now, question is, how do we do the braiding? Okay. And the answer is, the braiding can be done just as it can be done in the toric code. Basically, you have amoeba-like motions. So what you do, you remove one generator on the back of where you want to move and add it to the front. And so this way, you can, without reducing the, too much, reducing the weight of of this logical operator, you can move defect around. And you have to move it in a right way in order to braid it. And generally, if you have two defects, they may or may not, after you move them around, they may or may not end up sort of being conjugated to each other. And that would be sort of the algebra of these holes. Okay. And so this takes me to the conclusions. And basic statement is that you have surface codes, which are actually very, very good. And the only issue with them is that they have big overhead. Now we are trying to construct better codes, and so the geometry, the corresponding geometry that would be needed, for example, you have square lattice with additional jumper connectors between the qubits on the square lattice. And so if you can operate these jumpers simultaneously in parallel, then you can enable the operation of more efficient codes, which would be able to encode more qubits. Okay, and sort of quantum LDPC codes are very rare because you have to have matrices with small weight, and that such that the rows are orthogonal. And sort of in information theory, it is very well known that in the corresponding ensembles there are very few of them. But nevertheless, there are algebraic constructions for these codes. And if any of these constructions, as long as you start with matrices of big enough distances, then you can have these defects that would enable protected operations within the code. And then sort of these are the questions that are sort of I'm working on and trying to answer. And one of them is if you have a finite-rate code family, so what is the algebraic geometry? What are the geometrical properties of these? Okay, and the statement is sort of this. In some cases, like hyperbolic codes, it's very similar. It's very similar. You just have planar geometry. But these non-local codes, very often, they can be rewritten on some hyperbolic graph, which would be locally higher dimensional. Okay, and so sort of I'm trying to do that and classify different classes of these. And then what are the homological properties or defects? And then also, is there a Chern-Simons theory that can be written down, even though these are non-local in the space, in the map to a local system on a graph? Is there a topological field theory that you can write for these? Okay, so.
Thanks, Neil. Now open for questions, comments.
I guess it's time for lunch.
All right, if not, let's thank Neil and all the speakers again.